for having me here. It's great to be here in the Institute. Yeah, so my title is about Enriques surface fibrations, and yeah, essentially it's going to be about like a counterexample to the integral Hodge conjecture. So before I sort of present the main theorem, let me just say something about the motivation for that problem, and why we're interested in fibrations in Enriques surfaces. So the setup is as follows. We take some fibration, so maybe X is a smooth projective variety over C. Maybe B is some smooth curve. Then, yeah, then you have the famous Graeber Harris star theorem, saying that if the general fiber XP is rationally connected, then F admits a section. So if you're more arithmetically inclined, then this means that X over K, or admits a K where K is the function field of this curve. And here, rationally connected means that, yeah, basically any 2 points in the fiber can be connected by a chain of rational curves. Okay, so of course this is a very deep theorem with many applications. So it's interesting to see, what sort of varieties that do admit K points, how restricted is assumption of being rational connected. All right, so there was a question of the Sarah in a letter to Grothendieck. So is the same conclusion. Does the same conclusion hold if the fibers are O secret? Meaning that you have no higher homology of the structure. So rationally connected varieties, they certainly satisfy this condition. And Sarah is asking whether, if you have a fibration over a curve where the fibers satisfy this, whether you always have a K point. Yeah, so Sarah immediately says that, well, this does sound very optimistic. And yeah, so it was shown by, let's say, Graeber, Harris, Murre, and Starr, and also Lafon, around 2000, that the answer is no. There exists Enriques over curves with no section. So for surfaces, the sort of the next, if you have something that's uniruled or rational, then it's covered by this Graeber-Harris star theorem. Yeah, so the next interesting thing is when you have Kodaira dimension 0 and Enriques surface. And then they do exhibit, even if it's not very explicit, they show the existence of certain Enriques surfaces defined over the function field of some curve where there's no section.
Can we require the integral homology to be 0? I mean, how to say that? If there's a semi-connected condition.
I'm sorry.
If we require semi-connected.
Simply connected.
No torsion. With this condition.
That's a good question. I don't think there's a known counterexample in that. Yeah, certainly for surfaces you need to go to general type or something for a counterexample. My guess is that it should still be counterexample.
Want to take a shot?
Yeah, that'd be great. Okay, so then there was this sort of new question by N and so is it still true that the index of f equals 1? So the index is the minimal degree of a zero cycle over B. So we have this map from X to B, and we're requiring that the degree map from Chow 0 over this function field is isomorphic to Z. So, even if there's no section, it could still be that there's a degree 3 curve and a degree 4, or maybe a double cover of B, so that they together sort of generate a degree 0 cycle of degree 1. So maybe this is maybe this is the right conclusion in the setting that we're looking at. And this is really what motivated our problem. So it's known that there's a result by Kodetuden and Voisin from 2012, I think, saying that for in the setting above, the push forward map from H2 of X to H2 of B is surjective. So in other words, there is a class, class in H2, which push forwards to the generator of this curve.
So can you just remind me what the index of that means again?
So the index is the degree of a sort of minimal zero cycle over the function.
Oh, I see. Okay. Gotcha.
Yeah. Okay, so this implies that there is no topological instruction to this question here. There is at least a homology class which has the right, or has the properties of
So I can conclude.
section.
So here, your question here is that question?
Yes, this one. Yeah.
No, is that question? I mean, is still true? Which one is still true?
Sorry, and then the next question is this.
No, you know, what's it in know? It is
Oh.
still true that.
Sorry. Sorry. Is it true that if you have such a fibration that the index is 1? So
The
it
index,
is specified here. So does it make sense? So instead of asking about a section, I'm asking if you have a fibration with acyclic fibers, is it true that the index is 1? Okay. All right. So at least there's a class which has sort of same intersection properties as a section. Okay, and furthermore, that would mean that a counterexample to maybe I'll call this question star. To the question star would give counterexample to the integral Hodge conjecture. So just to say what that means, it's a statement that all integral Hodge classes that this group is generated by classes of the algebraic subvarieties. Okay, so in this
So this is not a torsion class, this is a class that's not torsion. The integral Hodge conjecture.
Sorry, what?
Could be, you're constructing an integral class that's not torsion and not algebraic.
Yeah.
Okay, because I'm now beginning to see how this works. Okay, this is great.
Okay, so sorry, maybe that is something that's good to clarify. It could be torsion. I'm just taking the elements of this group that map to
Right.
to the KK piece. Okay, so to summarize, there is some. Okay.
Can you restate your Enos question in Chow 0?
Yeah, so I'm asking whether the degree map here is Z, is an isomorphism.
No, I mean the whole one, the full statement in terms of Chow 0. I mean Enos question in terms of Chow 0. Yeah. So you have a fibration.
Yeah.
The base and the fiber are Chow 0. Chow 0 degree 0 is 0 or is 1, or I don't know how to say that. And the degree of the base and the fiber are what? Are 1 or?
Okay, so we have a fibration over
So
here.
are isomorphic to Z, and then the total isomorphic to Z. This is the statement for the question. For Enos question. In terms of Chow 0.
Yeah, this is the whole
No,
statement. So,
that's one. What's the fiber? The fiber in.
oh, sorry, it's this condition here, acyclic. So I have a fibration where the fibers have no higher cohomology in that.
No higher cohomology. That's a requirement.
That's right. Yeah.
Okay.
So that's right. Okay. So yeah. So if that's not true, so if Eleanor's question, I mean, if there is such a vibration where it's not equal to z, where the degree map is not an isomorphism, then there has to be some cohomology class, which couldn't possibly be algebraic. And this is what led us to look at the integral Hodge conjecture for these Enriques surface vibrations. So let me just completely switch gears, like reboot. This is still in the, or this was the motivations section. So let me just write down what the main theorem is. Okay. So theorem. This is like Fumiaki Suzuki. So there exists smooth projective threefold X, which is a Enriques surface vibration. Such that the integral Hodge conjecture fails for X. Moreover, you can say that so X has another dimension 1, that's simply connected, and the cohomology groups are torsion. Sorry about the handwriting. Maybe I'll okay, so at least there's an Enriques surface vibration where in fact this does fail, this integral Hodge conjecture. So let me give you some context why you should sort of care about this statement.
So this is H4, which component is?
Yeah,
It's also free.
yeah. So for a threefold, there it's really just one degree where the integral Hodge conjecture could fail. It's the H4. Because for devices, you know.
I'm pretty confusing. So here, this the fiber is of quadratic dimension
0.
0, and the base is minus infinity, and the total is quadratic dimension 1.
Yeah.
It seems contradict to some conjecture, right?
I don't know what you mean, but okay.
I cannot recall the this one.
Okay, let me just continue. So first, I mean, there are some famous counterexamples to the integral Hodge conjecture. One is to Attia and Hitzenberg in the 60s, I think it's around 1962. So this is with torsion classes. So they exhibit some sort of degree 4 class on a quite high dimensional variety, which are not algebraic. And then we have more recent examples due to Golar, which is around 92, I think, where you looked at a threefold in P4 of very high degree. Yeah, so these have just Z in H4 non-torsion. So, in some sense, our example is, I mean, they're closer to Kolar's example. In some sense, it's harder to produce non-torsion examples because, you certainly couldn't use the techniques from Mathias Hillsborough, where they more topological. And then I should mention that there are some like positive results for threefold. One is due to, so the integral Hodge conjecture is true or holds if x is linear ruled, or the Kodar dimension, or let's see, canonical divisor is 0, and these two 0 is 0, so this is due to variables on. In other words, if you have a threefold with some simple geometry, like unit ruled or Calabi-Yau, then it is true that every Hodge class, integral Hodge class is algebraic. So this was improved by Totaro, or let's see, so x. So also, if the Kodar dimension is 0 and x0 of k is not 0, so you do have a section of the canonical level. So in particular, Calabi-Yau's, like abelian varieties or abelian threefolds, they do satisfy the integral dimension. So these results are really about either minus infinity or Kodar dimension 0, right? So our result really goes, I mean, it has this Kodar dimension 1 condition. So it's a counterexample, sort of, which goes just outside this range. Okay. And I should say again that this counterexample really is of sort of non-torsion type. So there's an example of a threefold with a non-torsion class, which is not algebraic, but 2 times the class is algebraic.
The critical fibers of this are important. How many?
In
This situation.
let's see, I think it's about 24 are critical points in P1. It's very explicit, so I'll describe it in a second. Okay, so I was thinking just to devote the rest of the talk to explaining what this threefold is. I mean, it uses some quite nice classical algebraic geometry, and it's a little bit funny to see where this abstraction to being algebraic comes. Okay, so this is the construction. Before I say that, sorry. There's one more thing which is very important. So, of course, this theorem on itself, maybe it's not something you would. Of course, it's interesting that such a threefold exists, but there's an interesting consequence. So this would be a counterexample to a question with Murre. So this statement is there exists so that the Abel-Jacobi map so the Abel-Jacobi map is a map from AT. This is it's the subgroup of Chow. So this is the P cycles, or codimension P cycles algebraically equivalent to 0. So it's a subgroup of the Chow group, and it maps on to, or it maps to the intermediate Jacobi. So B. So it's defined just using the integration. But the statement is that this is not universal. Okay, so yeah, for P equals 3. So when there's this whole thing in algebraic cycles that you always study Chow groups using sort of maps into abelian varieties, and people believe for a long time that that you would have a sort of nice picture, like in for the Albanese variety or the Picard variety, that you would have some sort of abelian variety that would control cycles that are algebraically equivalent to 0. So here there are some known results. So this is universal if P is 1. So this is the Picard variety, and P equals the dimension of X. So this is the Albanese. And it was also proved by Murre himself that if you look at codimension 2 cycles, then indeed this map is universal. So this result here is a deep result. It really uses some rather sophisticated tools in algebraic K-theory, like block the Mercury of the Suslin theorem. So it's a very, very non-trivial result. But our example really shows that this is the best you can do. I mean, it really fails in the next case where P is 3.
Sorry, what does it mean to be universal?
Yeah, so it means, I mean, I'll say a little bit more about this at the end, but so a priori there's no way to put like a variety structure on this thing here. But you could still, define group homomorphisms into varieties, and you can say that this is sort of universal among maps into abelian varieties. So any variety or any regular homomorphism into an abelian variety has to factor through this map.
And it has a Liebman Jacobi.
That's right. In fact, yeah, I was being a little bit sloppy here, but I'll make this precise at the end. What universal means. So that's the sort of main application here, and that we find this example. This is a fourfold example, whereas the main example is a three-dimensional example. So we still sort of, I'll explain this at the end of the talk. All right, so I'll explain this construction. Okay, so let me just do a quick recap of Enriques surfaces. So there's our surface is S, so that you know its fundamental group is C mod 2, and 2 times the canonical divisor is 0. So this condition here means that there's a K3 cover. Z to S, which is the finite total of degree 2. Okay, so these are very important in the geography of surfaces, but they're a little bit tricky to construct. They're not as explicit as K3 surfaces, which are cortex P3 or double covers of P2. So when we're constructing these families of Enriques surfaces, I mean, we're really like writing down equations for X. So for that, we need to actually work with explicit models for the Enriques surfaces. So here's an example, or a projected model. So let S be the subset of P2 cross P2, sorry, be defined by the 2 by 2 minus of a generic matrix. P0, P1, P2, P0, P1, P2. Where are the degrees here? So we're in the product of projective spaces, so I can talk about bi-degrees of polynomials. So the degrees of the PI, the T0. So typically here you have polynomials that only involve x's, and here you have 0, 2. So that would be polynomials, quadrics in y's. So it's important. Okay, so it's the 3 minors of this matrix, and this defines an Enriques surface. So it's not as nice as a Corte surface or anything like that, but it's rather explicit. All right, let's see. So this is not that well known that you can construct Enriques surfaces like that. So let me just quickly explain why this is actually an Enriques surface. So to do that, I just need to tell you that there is some sort of K3 cover. So a priori, we have something that's defined in P2 cross P2. So let I be Pi plus Qi in P5. Okay, so I'm taking the P5 where I just join these two sets of variables. Okay, so yeah, and I just define these quadrics here. So there's an involution I from P5 to P5, which is defined by just doing nothing on the x's and then flipping the signs on the y values. And well, the special shape of these quadrics means that they're all invariant. Like this one is certainly invariant, it's just involving the x's. And also this one is invariant because it only involves y's, but it's of degree 2. It's homogeneous of degree 2, so it is flip the sign of all the variables, it's still invariant. So that means that z constructing here is a degree 8 K3 surface. If I choose polynomials completely generically, this surface in P5 will not intercept the fixed point locus. As being the quotient of Z or I, it's an Enriques surface. And yeah, you just check that this Enriques surface embeds up there in P2 plus P2 by those equations. All right, so it's really explicit, like what these variants are. And this quotient construction will be important later. Okay, so now we have constructed Enriques surfaces. So let's construct the threefold. So this is the threefold in the main theorem. So let x be the threefold in P1 plus P2 plus P2 defined by the matrix where now I'm in a product of 3 projective spaces, so I put a tri-degree here. Okay, so it's a threefold that lives inside this fivefold P1 plus P2 plus P2. And you see that the first production is an Enriques surface fibration. Right? Because okay, here you have some x's and y's, and here maybe some maybe s and t or something like that. Then, and if you fix a point in P1, it's just the construction that we had before. Yeah, and if you choose these generic metrics, if we choose these polynomials to be completely generic, x will be smooth and yeah, have all these. All right, so it's a very explicit threefold. It's really just defined by three equations. Right, so let me just explain some of the properties of X. Of course, because it's so explicit, we can just compute all the invariants right away.
So I'm confused. So here your degree of P1 is 2, P2 is 0, right?
Yeah.
0, the 0 that means constant, right?
Yeah. No, it means yeah, it means constant if you want. Yeah.
Then how to take the minor? The P1 Q2 P2 Q1 this degree is different.
What?
P1 degree 2, right? Q2 degree 2, P2 degree 0, Q1 degree 0.
Maybe you're sorry. Maybe you're misunderstood.
So what's the meaning? Why?
No,
So P0 and all of these they look sort of like S X 0 squared blah, 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 and then Q0 would look like S Y squared. So it just means that there's a linear term in that the polynomials on P1, and then they're quadrics on the P2. And
everything quadrics.
yeah, so
But the coefficient is of degree 1.
yeah, exactly. Yes, that's right. Yeah. Okay, so let's see. So we have some properties of X. So first of all, X has codimension 1. You can see you can just compute basically from this description. X is simply connected. And it has no torsion in the cohomology. And this is not so obvious because the Enriques surfaces themselves they do have torsion and that they're not simply connected. So I mean, if you think of it, I mean, that really requires a computation. Maybe even more surprising is that Chow 0 is Z. Is it's also usually quite hard to prove these statements about the Chow 0, but it just follows from Bass and Lieberman's result that on an Enriques surface, the Chow group of zero cycles is Z, and we really have a family of Enriques surfaces over curves. Right, and then we have Hodge. The form 1, 0, 0, 26, 0, 0, 45, 0, 0, and etc. So you have zeros on the outer line here, and so indeed the generalized block conjecture tells you that this is expected.
Yeah, the motive of X degenerates.
Sorry. Oh, yeah. That's right. Yeah. Maybe I'll say a little bit about this number here, because it's related to your question about the singular fibers. So here's the reason for large Picard number. So just like here we really constructed the Enriques cover explicitly. We can just do this in a family. So let's take y0 to be the zero set of all of these f's. So the f's here are just the sums of these. Well, f0 is p0 plus q0. So this lives now inside p1 to p5. So this via p1, it's a k3 surface vibration. But so I said before that generically, if you take this, if you take generic coefficients, then this z up there will not intersect the fixed point locus. But if you take a one-dimensional family, then some of them will intersect these two planes of so here what you do, you blow up the fixed locus, which is P1 across two planes. So that it's an involution on P5, so there will be two planes which are fixed under involution, and you blow up P1 across this thing here. And then there's a double cover. Or if you want, the involution acts here, and when you blow up, the action extends to y, and then you can take the quotient here. So this is our x. And in fact, this is the picture that you use for all of these computations of Hodge numbers, for instance. Yeah, so it's very important, this blow up thing. So let's call this pi. So pi blows up 12 plus 12, 24 points. Okay, so maybe I'm going a little bit fast here, but there are two planes in this fixed locus. So we have these two planes, and for each of the plane you have 12 fixed points. So I really group them together as to which plane they appear in. And from here we get 24 exceptional divisors, which I will also group like this. So it will be E, I, J, where I is 1 or 2, and then J will go from 1 up to 12. All right, so then we can also see that P is just ramified exactly along these exceptional divisors. So we have these distinguished 24 exceptional divisors on X. And well, we start with something which has Picard number 2, P1 plus P5, it's a complete intersection. And then we blow up 24 points. So this has Picard number 26. And then we take the quotient, and we can show that we do get 26 in the Picard.
What's the Picard number of the K-tracer?
Oh, 2 here.
And 2, okay.
Yeah, so you mean the K3 vibration, that's Picard number 2. Yeah. Just by Lepsch's hyperplane theory. All right. Okay. So we have a goal to exhibit non-algebraic integral class. On the threefold, and the strategy is the following. Find or beta such that beta times all of these exceptional divisors is 0, and the degree of beta over P1 is 1. So this is just like in the question we had in the introduction. We want a homology class which sort of looks like a section. It has degree 1 over the P1. We really want this thing to be orthogonal to all of the exceptional divisors. And B, so we prove a congruence for all curves C in X, namely that the degree of C over P1 is congruent to C times sum of the exceptional divisors modulo 2. Yeah. Okay. Let me explain this. So we have these two sets of exceptional divisors. They're grouped according to which plane the fixed point lies in. So here there's so first this thing here, finding a class like that's sort of easy. You're just writing down. I mean, we have a complete description of the H2 of this family. So finding such a class is easy. Just follow some hyperplane here. So now B, this I mean, in some sense, B and A and B, there are difference between like algebraic geometry and topology. So this is a purely topological thing. Whereas this inequality, this equality is supposed to hold for curves. So I'm saying that the degree of the curve over P1 should be congruent to the intersection number with this this fixed divisor here. And this sum here, there I'm really just fixing one of the planes. It's not all of the exceptional divisors, it's just sort of the ones that are fixed or supported on the same plane. And well, you see that these two contradict each other, right? I mean, this class beta couldn't possibly be algebraic if it's orthogonal to all of the exceptional divisors and still a degree 1 over P1. So this is sort of the interesting part. This is easy. So I realize I don't have time to prove B, but so B uses degeneration argument. I think it's a pretty fun argument. So we have x over P1. It has all these exceptional divisors lying on it, and because everything is just defined by a 2x3 matrix, I can write down like a special matrix where this family just breaks up into like pieces. So what we do is to degenerate to a very, very singular vibration. So basically it looks like this. So there's a family over some disk where the special fiber looks like this. So we have x0 and x0 prime. And yeah, you still have these exceptional divisors. Okay, so we're really degenerating to something that's very, very singular, and we try to analyze this union here. So basically, the argument goes like this. So if this congruence is not true, there's some curve where this equality does not hold. But if I just want to prove this for the sort of very general element in the family, if I have a curve, a counterexample on the special fiber or this generic fiber, then it has to specialize to a counterexample also on this thing. But the thing is now that these exceptional divisors, they all live on 0, so it in particular avoids this other component. And we just analyze this situation here and see that we can sort of more easily prove the congruence here. I think this is sort of the takeaway part of the proof, that we degenerate into a union and prove this congruence on the union instead of on the generic K3 Enriques fibrations.
So in some sense you are using that the curves, they do not disappear by degeneration?
Exactly, yes. You can always take the flat limit of a family of curves. So the counterexamples on the generic one, they have to sort of have some sort of limit on this thing. Okay. I realize I have only about 5 minutes left, so maybe I'll just say a few more words about the application. I'll make this brief. All right, so we have the Abel-Jacobi map, which is just the map from APV. So this is algebraically equivalent to 0 to JP, which is Jacobian here. So we let JP of A be the image of this map psi p. So this is the Lieberman Jacobian. And this, while this is not in general an algebraic variety, this one is always algebraic. So this is an abelian variety. And also, let's see, so also this map is irregular. So I don't think I have time to define that, but it's some sort of we just don't. So a priori, this is just a group, right? So the irregular homomorphism is meant to sort of say that this is close to being algebraic in some sense. We just don't consider all possible maps groups. Okay, so Murre's conjecture was this Lieberman-Jacobian is universal among maps AP to an abelian variety. So anything here has to factor through this Lieberman-Jacobian. Okay, so I mentioned that this is okay for p equals 1 in the dimension 2. So finally, I'll say what happens for our example. So there's a result by Walker saying that this Abel-Jacobi map factors as so we have A3 to be to intermediate Jacobian of a mixed Hodge chapter from the Oslo equation. So here's our map, the Abel-Jacobi map. And what I'm saying is that there's a different abelian variety here that factors the. So by universality, we really want, or we expect this one to be an isomorphism.
This is general, or just for some example of V that you have constructed from your.
Oh, sorry, this is pretty general, but let me say that it at least holds for p equals 3. In our situation, but it's so far I haven't even said what V is for our example. So we apply this to E S times E, where E is a very general elliptic curve. That's a fourfold. Okay, so so basically we get by the results of Suzuki, then if this is universal, it implies that the kernel of 3 is 0, which means that So in basically we have our example, and we managed to factor the Abel-Jacobi map via a different abelian variety, and then we can sort of relate the kernel of this map to the failure of the integral Hodge conjecture. Not of V, but really just sort of X times.
So the Sado-Picard varieties is what I was thinking of, which are conjectured to be exogenous to the Abel-Jacobi.
Okay.
And the Sado-Picard varieties are actually motivically defined.
Oh.
And one wonders if they are in fact universal. So,
Yeah.
something to look at.
Yeah, right. You said that they're using the incidence.
It's equivalence, yeah.
Yeah, we should discuss it later. Yeah. Anyway, so that I think that's the what I wanted to say. So yeah, thanks.
Questions for the speaker?
So what's your N2? N2?
What? Oh, this one? Yeah, this is the Conniveau filtration on cohomology. So you have a filtration on integral cohomology by classes that vanish on an open set, and you filter it by the codimension of the complement of that open set.
So in the beginning, so how to prove this Chow is zero in your case? That's it.
Oh yeah.
It seems there is no general result, right?
No. We really use the explicit geometry of this vibration. So we use the fact that this is an Enriques surface vibration, and then there are many deep results that enter the picture, like this Bas-Lieberman result, the decomposition of the diagonal, the Reutemann theorem also enters. So it really uses a sledgehammer for that statement. Even in
So
this
I mean, in general, a surface with Chow zero, with Chow of 0 cycles is 0 over curve over P1.
Yeah.
So can you prove the total Chow zero is Z?
No, I don't think so. I mean, the result by Bas-Lieberman that we're quoting, that uses Enriques surfaces. So yeah, otherwise you would you need the full block conjecture for a surface, and of course that's an open problem.
So no example, right?
No counterexample to the block
No
conjecture.
Generic for you means Zariski open set or outside enumerated set?
Yeah, that's a good question. So I mean, the conclusion that we get is really for very general, because we're using this degeneration argument. So we're really saying that it's outside a countable union of closed subsets.
If I ask you explicit example, you would not be able to give me then.
That's also, so we work over Q, so we can write down explicit things over Q in fact.
And you have explicit examples of this.
Yes. So the proof that I sketched here works for very general, but we write it out for explicit examples over Q. Yeah. So you'll have to take a look at the paper if you want though.
More questions? Let's thank the speaker again.